actually. We're starting chapter 13 today, which is the last chapter in the textbook.
The mango dragon fruits.
So chapter 13, we're recording. My microphone is on. My batteries are charged. And I have my drink. All right. We are now in the last chapter, right? Chapter 13. And I don't have the title of the chapter, I'm sorry. Vector calculus is what I'm guessing it's called. And the first section here, 13.1, is very short. It just introduces you to this idea of a vector field. All right, so a very short chapter. It's a very basic concept. Let's see how you do with it. So we now define something called a vector field. And here we're going to have vector fields in either two-dimensional space or three-dimensional space. We're starting with two-dimensional space. So in two-dimensional space, we let D be any set in the plane. So imagine you have a set of points in the XY plane, right? All these points. And then let's say we have some domain here. Maybe it's the whole space. Maybe it's just the first quadrant. Maybe it's a circle in here. Wherever it is, that's D, capital D. So let D be a set in the plane. A vector field on that domain D is a vector function, capital F with that little half arrow on top of it, that assigns to each point in the domain a two-dimensional vector. So at every single point, we create a vector, and it's two-dimensional. So here, for example, and this is like an example of a magnetic field. We could say that at this particular point, the magnetic field is applying a force in that direction, and the length of the vector would be indicative of how strong the force is, right? That makes sense? Now, we can look at another example would be like a topographical map. So this is a map of like a hilltop, like here's a hill, like a couple of hills. And if we look at that from the top, we get these things called topographical maps, which these are all elevation lines. So it shows, anything on this line is all at the same elevation. Anything on the next line would be at a different elevation, and so on and so forth, right? You all seen these before? Yeah. And so at every point, you can imagine a vector that would maybe represent, we've talked about this, if you like put a ball there and let it go, like where it would roll. Okay, so that vector, you could define a vector field that would give you all those little arrows all over the place, right? That's just two quick examples, magnetic field and contour map. But in general, it's pretty much anything we want it to be. So here's an example of a vector field up here. The vector field is written capital F, right? And then we said any two functions here. So I'm going to put, this is a specific example, all right, of a vector field. So there it is. Two-dimensional vector field. It's negative y, x. So what would the vector be for this vector field? What would be the vector at the origin? Well, that would be at the origin, at the point 0, 0, we have that the vector field is going to be equal to the vector 0, 0, right? And so there's really kind of no vector there. It's just a point, if you wish, right? How about if we move, let's go to the right, let's just go to the point 1, 0. So what would be the vector at 1, 0? Mm-hmm. It'd be 0, 1, wouldn't it? It'd be 0, 1. So that would be a vector that points directly straight up and actually has a length of 1, because the length of this vector is 1. So at 1, 0, if I move out to the right, 1, 0 right here, the vector that corresponds to that point goes up 1, like that, right? How about at 2, 0? What's our vector field vector going to be there? 0, 2. So as I go out to the right, this vector still points straight up, right? But now has a length of 2. And if I went to 3, 0, it would point up 3, right? All right, that's what's happening along the x-axis. How about in the other direction? How about like if we go to like negative 1, 0? Our vector field would be 0, negative 1, right? So now it's going to look like this, right? And if we go to negative 2, 0, it'll go like that. Y'all agree?
Yeah.
And we could keep doing this, right? Let's do something more interesting. How about along the y-axis? If you're along the y-axis, then what's your x-coordinate? 0, and then what about your y-coordinate here? Let's go with, how about 0, 1? So what's the vector that would go with at that point? Negative 1, so we're plugging in negative y here, so negative 1, 0, like that. So that's going to point which way? To the left, right? Okay. So at 0, 1, it's going to point to the left like this. Right? Okay. Now, we could do this all day long, right? At every single point, we could pick other interesting points like 1, 1. Let's do one last one. What would happen at 1, 1? What would our vector field be? What would our vector be? Negative 1, 1, right? So at 1, 1, we would have a vector here that points left 1, down 1, right? So it'd be like this, something like that. Oops. Up 1, sorry. I said up. Left 1, up 1, like this. Okay. Yes?
Yes.
Okay, so what we can do is we can imagine, we can let the computer do this for us. I can sit here and I can have the computer do these for us, where I can move around, and it's going to go ahead and calculate it and draw me all those vectors. Okay? Or I can just say, give me a basic idea of what's going on here. And this is a plot of, the computer has basically taken its own points and it's created vectors for them. And it's not really concerned about, like at 1, 1, it's not saying that, it's not giving you that exact vector. It's giving you, what it's trying to show you here is that as you move to the right, the vectors get longer, right? As you move to the origin, they get smaller. And they seem to have some sort of like turning effect. Like this vector field seems like if you were just like to let something go in here, it would start rotating around, right? But if it was closer to the origin, it wouldn't quite be as fast, right? That makes sense? Okay. Let's change the, you want to change the vector field? Sorry, my phone keeps vibrating. I'm like, what the hell's going on here?
Is he texting anybody again?
No, it's actually my daughter. Let's do a different vector field, all right? But I'm going to actually do one where we get to make it up. Okay, so any vector field you want. So who wants to make up a vector field? What do you got?
Negative y squared.
Negative y squared?
And 3x.
Okay, and then the other one, 3x?
Yeah.
How about I add 3x in there, like that? Because you can have x's and y's mixed. You want to do the y component?
Yep, sure.
What?
4 cosine x
4 cosine x. Okay, that good?
plus 1.
+1. All right, there we go. Okay, so let's do that. So negative y squared, and then plus 3x. And then, yes, it's okay. We can do that. And then for this one, we wanted 4 cosine of x and then plus 1. Here we go. So I'm gonna start having the computer do this for us. So as I move, look at our vector. They're pretty long already, aren't they? So along the x-axis, that's what's happening. And then in the y-axis, it's hard to see it. So let's have the computer give us kind of a picture of what's happening here. Let me go. Well, it's really strange looking, isn't it?
Yeah.
Yeah. So seems like up here we have this very strong field up here going this way. Here it's strong, but do we have any weird changes in direction? I'm going to make this bigger. Maybe we can. No, I wasn't sure what direction. These are both, this is pointed down, like this way. This one's up.
The other one that's below that, below the arrow going down, is also going down. It's just the opposite direction.
Yeah, so, I mean, it's weird. It is what it is, right?
Yeah.
It's a vector field. Let's change something in here. Let's do this. See where you have cosine x? Let's make it cosine x times y. That didn't really have too much of an effect, did it?
No.
Didn't look like it. How about we make this one sine of x plus y? Oh, wow. Okay, so that had an impact, right?
Okay then.
So all we need to know here is that in two-dimensional space, we can define vector fields. You can define a vector field however you want to define it. But what it does is at every single point in that domain, you now have a vector. You can't, if you drew all of them, then it would just cover the whole space up and you wouldn't be able to see. Does that make sense? But at every point, there is some vector that corresponds to that point. All right? So now, in three-dimensional space, we have a similar idea. Okay, if you have a domain, this time we'll call it capital E, it's some domain or set in three-dimensional space, then we can define a vector function capital F such that at every point x, y, and z, we have this three-dimensional vector function. So this is a model of the magnetic field for the Earth. And so at every point, there's some direction, right? Some direction vector. Now, it's much harder to do this on a computer, okay, because in three-dimensional space, as we know, drawing three-dimensional on a flat sheet of paper is hard enough. You know, trying to show a vector field in three-dimensional space, right? I mean, it's difficult to grasp it. But the idea is just that at every point there's a vector, right? If you get too many vectors in there, it just gets too hard to see it. All right? Okay, I'm going to turn this off. And this right here happened to be that vector field. It was just negative y, x2, z was that vector field that I just showed you. All right, here's an interesting vector field. This one is actually useful. So can anyone tell the interesting characteristic of that vector field? What is that divided by the square root of x squared plus y squared plus z squared?
That's p squared. Rho squared.
That's just room.
No, that's rho because it's
So imagine I go out to some point. Here's x, here's y, here's z, right? I go out to this point x, y, z. And I plug it into this particular vector field. What is the square root of x squared plus y squared plus z squared? What would that be? The distance what? From that point to the origin, isn't it?
Yeah.
Isn't it the distance from that point to the origin? So that distance right here, you know, from there to that point, that distance right there, that's what this is, right? So what you're doing is you're taking each component of the vector field and you're dividing it by the distance. Okay. Should be a unit vector then. This should be a unit vector. That means that this vector field always spits out unit vectors. Always. Do y'all agree? It's always going to spit out a unit vector, except at the origin. At 0, 0, 0, this is undefined, right? But otherwise, it's going to spit out a unit vector. Can you tell me something about that unit vector?
It's always going to be opposite.
It's pointed in what direction? Towards the origin. Now, why is it pointed towards the origin? But yeah, look, if I just asked you what the vector x, y, z would be. Okay, so we go to the point x, y, z, right? That's a point. What would the vector x, y, z be? It would be the vector that goes from the origin to that, right?
Yes.
That's the vector x, y, z. So this is spitting out a vector that points in the opposite direction of this, right? The opposite would be negative, negative, negative. So that would point in the opposite direction of this vector, but it would have a unit length of 1, right? So it would be like if you move out to any point in the space, it's going to draw you a vector that points back to the center and has a length of 1. What do you think this vector field is very good at representing? Gravity. Right? It's going to be a center pointing vector field. It points back at the center of the object. Now, what we do on Earth is, right now this is going to give us a unit vector, right? It's going to give us a unit vector pointing. Everything's going to point in. Whoa, too many. Yeah, there we go. There they all are, right? Notice they're all the same size, like thickness. Notice there's no change in the size of these vectors. That's because they all have the same unit length. They're all pointing to the center. On Earth, what we would do is we would just put some sort of constant in here. C times, C times, C times. And that would basically change the length of that vector for your gravitational acceleration on that planet, whatever planet you're on. So C can be adjusted for wherever you are. Make sense? Yeah. But the field itself is what you could use for any object with gravity. So that's an important vector field. And that's an example of a three-dimensional one. All right. So now we move on to the next idea. Remember that we have been dealing with surfaces, hadn't we? F of x, y. Z equals f of x, y. Was always some surface, right? Right? Some surface. This is our function f in three-dimensional space. So whenever we had a function of two variables like this, we had defined this thing called the gradient of the surface. And the gradient was just a vector, right? You took the original surface and you created a two-dimensional vector from this surface called the gradient, and it was just a partial of f with respect to x, partial of f with respect to y, and it created this vector function, right? Well, that vector function, that qualifies as a vector field, right? It is a function, it is a two-dimensional vector function. So you could say, yeah, that's a vector field. And if you have a three-dimensional scalar function, which we can't visualize here, then we have this thing called the gradient, which is now a three-dimensional vector function. In both of these cases, these are now called the gradient vector fields that are associated with the scalar function. So anytime someone hands you a two-dimensional or three-dimensional vector function, scalar vector function, you can always create its gradient vector field by just doing the gradient. And so let's see what that looks like. Okay, so here is an example of a three-dimensional surface over here on the right side. And remember the gradient always gave you the direction of steepest descent. This was like one of the big results when we were talking about directional derivatives. We said if you're standing on a surface and you want to know which way to point that you get the steepest descent, it turned out that it was the direction of the gradient vector at that point. So here's our surface in three-dimensional space. All right, this is our scalar function, little f. If we take the gradient of this, we will get a vector field. And over here on the left side is a picture of that vector field. And we can take a look at it like this. I think that's, yeah. Can you all see the vectors okay here?
Yeah.
So I'm going to move on this surface. I'm going to move, kind of backwards, other side. So can you tell that I've kind of gone off that back edge of the surface back there? So I'm kind of almost like rolling off the edge here. So if you were back here at this point, your direction of steepest descent is the direction of that vector right there, which corresponds to the gradient vector. So this is your gradient vector field, all in here. And that point right there, corresponding to this in two-dimensional space, is that vector. Yes? Okay. So now we have a definition. And this definition always seems to cause students issues. The definition of a conservative vector field. A vector field, capital F, is called a conservative vector field if there is some scalar function, little f, such that the field is equal to the gradient of f. I'm going to, yes. So this just means that the vector function is the gradient of some vector. This just means that the vector function is the gradient vector field of some scalar function f. So let me just illustrate. Let's say we have this. Let's say we have this scalar function. This is a surface, right? Okay. Let's create a vector field from this. So we're going to define this vector field. I'm going to define this vector field to be the gradient of that. So what is that? So the gradient is the partial of that with respect to x, comma partial of that with respect to y, right? With me? Okay. So now this vector field, right? This vector field came from taking the gradient of that scalar function, right? Okay. So let's just back burner that. Back burner it. Just keep that in your mind. I'm now going to show you a vector field. Here it is. See this vector field? Is it conservative?
Yes.
Why?
Because it's the same as the gradient.
Where we can say that this vector field came from taking the gradient of some scalar function. All right? Now we know that because that's the way I generated it over here. But imagine that you were just handed this to begin with, and we did none of this work, right? And you were asked, is this conservative? Is that conservative or not? Then you would have to figure out, can I come up with a little f that when I take the gradient of it, I get that? Do you understand that?
Yes. And by doing that, you take like the anti-data.
Yeah, we're going to have a procedure for that.
Okay.
And then later on, we'll have a quick way of checking. It'll be super fast.
Okay.
But for now, the idea of a conservative vector field is that it comes from the gradient of some scalar function. That's what makes it conservative. Is there a question? So in general, if I just put a vector field, you know that one that you gave me a second ago? You came up with this one. It was like y squared, negative y squared plus 3x, and then it was like 4 cosine of x plus 1 or something like that. Is that conservative? I have no idea. I'd have to go check, okay? And what I would need to do is find a little f. I'd have to find this, okay? Such that when you take the gradient of that, you get this, all right? So right now, it's not easy, not super easy for us to just look at a vector field and determine if it's conservative, all right? But we'll see later, even I think we'll see it today, that we really like conservative vector fields. Conservative vector fields behave extremely well for us. They make things a lot easier in our lives. All right, that's it. That's it for this section. So don't worry too much about this homework. I think it asks you here to like maybe try and graph some vector fields. Just do your best, you know. You know how I had plugged in a couple of points and tried to draw some vectors? Do your best, but as long as you understand the idea, we're okay moving on to the next section. All right. Line integrals. Or curve integrals. So let me show you what this section is asking us to think about. Let's say that we have a surface in three-dimensional space. Okay, we've got this weird surface. We already have talked about finding the volume under this surface, right? Like if you give me a domain on the ground, I can find the volume. If I restrict the domain like to this curve right here, I can find this. These are, if you just plug these points into the surface, you get this blue curve on the surface, right? Do you all see that? So we can use Lagrange to figure out the max and min values, can't we? But that's not what we're interested in here. Okay, so imagine we take this surface, we restrict it to some curve on the ground, and look at the image of that curve up on the surface, and then here's what we want to do. We want to take it, and we want to imagine dropping like a curtain straight down from that curve. All right? That green curtain is hanging from that blue curve up there, down to the ground. What's the area of that green curtain? Right, so it's not a volume question. This is an area question now. Does that make sense? Okay. So the way we're going to do this is a little weird. We need to first, I guess, understand that drawing this curve on the ground can be drawn using a vector function. So you see this red curve down here? I can draw that using this good old-fashioned vector valued function in two-dimensional space. We talked about this. These are called space curves. These draw curves in two-dimensional space, right? So this thing on the ground, this is now our domain. Our domain is this curve where we restrict our t between two values. So all I'm saying is we first need to be able to draw the curve on this, the curve that's going to be plugged into the surface on the ground. And the way we draw it is by using a vector valued function. All right? Yeah. Okay. So let's go back to Cal 2 and think about how we did this in Cal 2, because this is actually kind of like Cal 2. See, in Cal 2, you didn't realize it in Cal 2, but when you were finding the areas under curves, you were looking at it from the side like this, right? That's the way you were looking at it in Cal 2. You didn't actually realize that your curve was in three-dimensional space. So you were just looking at like X and Y. We're doing the same problem here, just now we're in three-dimensional space. And so can you see how we were actually hanging a curtain from a function? That's what we were doing. But the key here was that this curve on the ground was a straight line. All right? So what we did in Cal 2 is we said the way we're going to do this is with Riemann sums. And we're going to cut this up into a bunch of rectangles, right? An infinite number of rectangles. We're going to find the area of each rectangle. We knew that the height of the function, or the height of the rectangle would be the function's value at x. So you go to some value x, and that would be your height, right? That would be the height of the function from here down to here. Yes? And then how wide was it? How wide was it? That's your dx, right? That's your dx. And that's why we did the integral of f of x dx, and then we went from a to b, and that was our endpoints a and b, right? So that's Cal 2. So what changes now? I mean, what's gonna be the big difference? Let's go back to the picture of the curved looking one. I'll leave that there. Yeah, our domain on our ground is no longer a straight line. So I still want to imagine cutting this into rectangles. right? Cutting into rectangles, like that. So each rectangle, how tall will it be? Well, it's still the function's height, right? The function's value will be our height, but our function is a surface. So this will be f of xy, right? You give me the x coordinate, you give me the x coordinate and the y coordinate, and that'll give me some point in here. And then I plug that into the surface, and that'll give me the height of the function. The question becomes, how wide is this thing, though? How wide is this? It's not a straight line anymore, right? No? So how can we handle this? Everyone got the basic idea of what I'm asking? Okay, so here's how we're going to handle it. Let's just look at it from the top. Where is it? Oh, it's such a small little. There we go. Okay, there we go, right? So the top edge of our rectangle is right here, or we'll say the bottom edge is like that, right? So what we're doing is we're going to approximate this straight line right here by, we know it's a curve, right? In reality, our rectangle almost has a curve on the bottom, right? But we're going to approximate it with a straight line segment between those 2 points, between these two. And what did we use in Cal 2 whenever we were trying to do something like this? Where we had maybe we had a curve like that, and we were trying to estimate the length of this curve. We would estimate it with a straight line segment. And then as these rectangles get smaller, right, this straight line basically approaches the curve. This was arc length. That's what we used, arc length. So this right here is not going to be dx. It's not going to be dy. It's going to be the arc length. And the arc length we will call ds. And s is the standard letter we use for arc length. So this here is ds. And if you go back and look at your Cal 2, that is the square root of dx dt squared plus dy dt squared dt. This is what ds is right here. Now, would you like me to go through where this comes from, or are we? I don't mind going through where this comes from if you want. Yeah, I can show you. Okay, let me just. I have to go back and look at it from a Cal 2 perspective. Yeah, we'll do it this way. So, imagine that I have a vector function. And it draws me a curve, right, in two-dimensional space. And let's get t is between a and b. God dang it. All these stupid markers. I'm going to go and get new markers in a second because this is ridiculous. So let's say we have some curve, goes like this, right? So it starts, this would be where we are at the beginning, and this is where we are at the end. If I wanted to estimate the length of this piece right here, let's just say some little piece like that, if I want to estimate that, then what I could do is estimate it with the hypotenuse of that right triangle. Okay? So this right here, from here to here, is how much my x changes by, and this from here to here is how much my y changes by. So I'm going to call this dx and this dy. All right? Then the hypotenuse of this would be what? Dx squared plus dy squared is equal to that squared. So I take the square root of that, and that would give me the square root of dx squared plus dy squared. Does that kind of make sense? Now that's not what I have here, though. So there's something I need to clarify here before we can get to this formula, and that is this. When I say dx here, I'm saying how much x changes by, right? here's what x is, here's what y is. So I'm going to write down what x is. X is x of t, is that function, right? If I say to take the derivative on both sides of this with respect to t, the left side would become dx dt, and the right side would become x prime of t. Does that make sense if I take derivative with respect to t on both sides?
Yes.
Okay. Now, solve this for dx. Dx is x prime dt, right? And now let's put that in here, into this formula. So this will become square root of, what, x prime of t dt, but that what? Squared plus, and then the y would work exactly the same way. So you would get y prime of t dt squared. Now both of these have a dt in them, right? So this is going to be x prime of t squared times dt squared plus y prime of t squared times dt squared. I can factor out a dt squared and then take that out of the root as a dt, right? So that's where this dt comes from, right? So after I pull out the dt, put it in the back, I'm still left with here x prime of t squared plus y prime of t squared, right? That's what would happen if I pulled the dt's out. But what is x prime? Dx dt, and y prime is dy dt, and that's the formula, all right? So the infinitesimal little hypotenuse that will approximate that length is going to be this piece right here, ds. And then what I want to do is I want to add all those up, right? I want to add them all up. And what do we use to add things up? Addition, yes. How do we add an infinite number of things together in calculus? The integral, right? So the area of this thing is this times this, and I want to add them all up. So our new notation is going to look like this. We're going to do an integral over some curve C. And it's going to be our surface, which represents the height of our rectangle, times the width, which we are going to use the notation ds. This now is the notation for the area underneath, well, hanging from the curtain, right? That's our notation. I have this all in the notes, so I'm going to just go to the notes right now. I just was trying to get you to see where the formula comes from. Okay, here we go. I think this is the last version of it. Let's see. Yeah, that is the final version of it right there. So this is it. Right there. Okay, so this says that, let's say that you can draw the domain on the ground, right? You have this domain on the ground C. That gets plugged up into the surface, and up here you got something, and you're going to drop that curtain down, right? Then if you want to know the area of this curtain, this is the way we write it. We say we want to do the sum, the infinite sum over that curve C of the heights of the rectangles times the widths of the rectangles, which is really the hypotenuse of the arcs on C, right? We're just going to add these up. Now, what is the actual computation that you have to do? Well, the integral is going to go from A to B. Now, A to B is your restriction on T that draws your curve on the ground. Okay, so the limits of integration will always be dictated by the starting T and ending T for drawing the curve on the ground. You will plug into the surface. The x and y coordinates will be the x function and y function from your parametric representation or vector curve. And then this part right here, you're going to have to take some derivatives, take square root, all that stuff. and you're going to integrate the whole thing with respect to t. This is called the line integral with respect to arc length. So that's what it's called, the line integral with respect to arc length. I think most of you are okay with the idea that of this part right here, with respect to arc length, is the ds. Does that make sense? Calling it a line integral is the part that I think has always been weird. Like, why is it called a line integral? We're not integrating over a line, right? This c is a curve. It could be a straight line, yes, but it could be a curve. So this, but that's what they're called, okay? Sometimes you'll hear them called contour integrals instead. Contour integrals, because that's more like a contour than it is a line, right? All right, so let's do an example. And I think what I'm going to do is I'm going to put it up here. I'm going to go get some fresh markers because it's going to be miserable for me to continue with those. Let's see if you can take what I just said and take that one all the way. I'll be right back. All right. All right, so how did y'all do with this so far?
I didn't write anything down, but I have an idea of how to solve it.
Okay. So what do you think we need to start with?
Finding the boundaries, maybe?
Okay, like you mean the limits of integration?
Yeah.
Okay, which means we need to know C, right? We need to know how to draw C.
Yes.
How are we going to draw C with a vector function? That's what we need to do to start. So what does C look like?
C is the upper half of the unit circle.
Okay, so we need to draw that curve, right, with some vector function r of t. So some two-dimensional vector function that draws that. And this is going back on what we've done in this class. There should be something in your brain that, I guess, clicks here. How do you draw circles? Cosine and sine, right? So cosine t sine t would draw a unit circle. That would have a radius of 1. And t here would be need to be restricted between where and where? 0 and pi. That will draw me my unit circle, half of it, and it will actually draw it like this, right? It'll start here, it'll go kind of like a counterclockwise like that. That's the way it would draw it, okay? That direction will matter later, okay? That's why I'm pointing this out. So this is C, all right? That's C. So remember, what's happening is we're taking just the points in here off this curve, we're mapping them up into this surface, right? And then we're dropping a curtain down trying to find the area. So do you remember when I started class, I showed you a picture and it showed the curtain? That's this example. That's exactly what we're doing right now. That's the circle on the ground that we're drawing. So we're trying to do this. So what is our function? What is our surface function, f of x, y? What is it for us here? 2 plus, that's all right, 2 plus, this is the surface, right? This is the domain. These are the points that are getting plugged into that surface. Right? Okay. So we're trying to do this. D little s. Later on, that will be capital S. So little s right now. Right, so this right here, to do this, what we need to be able to do is have some limits of integration. So these are our restrictions on t, which we know are going to be 0 to pi, right? Then we need the function evaluated at x of t, y of t. I'm just writing the definition out right now. Then times the square root of dx dt squared plus dy dt squared dt. Right? So that's what that's the formula we're using. We know a and b, yes? 0 and pi. Do we know x of t? What is x of t? And what is y of t? Yeah, those are our parametric equations. This right here is x of t, and this right here is y of t, right? And so I think we can plug everything in. We're going to take our scalar function f, we're going to evaluate it at x of t, y of t. So that means everywhere we see an x, we put cosine t. Everywhere we see a y, we put sine t. And then we're going to do times the square root of the derivative of that with respect to x squared, then the derivative of the y one with respect to t squared, right? So there's a lot of things, I guess, for us to fill in here. Integral 0 to pi. Now our function evaluated those two parametrics. So 2 plus what? X squared. So cosine squared t times y, which is sine t. Okay, all of that times the square root. Now, I didn't do the derivatives of these. I didn't write them out because I figured they're easy enough for us to do, right? So the derivative of x with respect to t would just be negative sine t, but then we're going to square it, right? So we're going to take the derivative of this, negative sine t squared, which is just sine squared t. And then plus the derivative of y with respect to t, which is cosine t, but then square it, so cosine squared t. And we got lucky, didn't we? Because sine squared t plus cosine squared t is 1. So that just happens to be the square root of 1. Nice. Okay, so we've got integral from 0 to pi of 2 plus cosine squared t sine t dt. And that we should be able to do pretty easily. Does it all make sense? Okay. So now, let's finish this integral off. I think we can go straight to an antiderivative here. The antiderivative of 2 with respect to t is 2t. And then we have, well, I need to think about this for a second. I'm going to use a basic u substitution. U is going to be cosine t. U is cosine t. The derivative of that is negative sine t dt, which I have. I'm off by a sign. Who has it? Negative cosine, negative, how about negative 1/3? Can I do that?
Yeah,
Negative 1/3 cosine cube t. Let's just double check. Is that, take the derivative of this. 3 comes out, right? Becomes cosine squared t. Then times the derivative of cosine t, which is negative sine t, which gives us that piece. And the negative and the negative become plus. So yeah, that should work, right? And we're evaluating this 0 pi, right? So let's plug in pi first. Pi goes in, 2 times pi, so 2 pi. What is cosine of pi? Should be negative 1, right?
Yeah.
Negative 1 cubed, which is still negative 1. So minus a third. Or sorry, minus a third. So plus 1/3. And now plug 0 in. Be careful on 0. Plug 0 in here, we get 0 for the first one. But then cosine of 0 is 1. So we're going to go minus a third.
Yes.
So we wind up adding another third to this. So 2 pi plus 2/3. That is the exact area of the curtain hanging from that surface on that domain C. All right? As you might imagine, this can become very ugly if this isn't nice, right? Like imagine if this would have been something else and we had to integrate that. So these problems have to be kind of made really nice for us in order for them to work. Otherwise, we have to go to a computer or something to figure them out. All right, let's move on. If C, that's the curve, remember, that's the domain. If the C is the union of a finite number of smooth curves, C1, C2, C3, Cn, then the line integral over the entire curve can be broken down into the line integral of the first curve plus the second curve plus the third curve all the way out to the nth curve. So if our domain on the ground looks like a bunch of curves put together, we can do them one at a time and add up the answers, as this example illustrates. Find the line integral over this curve C of 2x ds, so it's with respect to arc length, so we're finding the area hanging the curtain, where C1 is the parabola, y equals x squared from 0, 0 to 1, 1, and C2 is the line segment from 1, 1 to 1, 2. All right? Let's draw our C first. All right, C1 is the parabola that goes from 0, 0 to 1, 1. All right, that's C1. And C2 is the line segment that goes from 1, 1 to 1, 2. Straight up. C is the whole thing, all right? C is the whole thing. C1 and C2 put together, right? The union of those two sets is C. So C here is the union of those two curves. And what we want to know is the line integral over the whole thing. So the previous note just says we can do these separately, can't we? So we have to do two separate problems here. First problem we have to do is the line integral over C1 of our function with respect to arc length. and then our line integral over C2 of our function with respect to arc length. So let's start with the C1. First thing, how are you going to draw C1? So what is the vector function for this? And I'm going to call R sub 1 because it's for C1, calling R sub 1 of t. All right, so you know what? I was thinking about this the other day. Remember in the beginning of class, I was like, you know, would y'all like me to use these little sticks and call on people? And no one wanted to do that? We only have 3 weeks left, so we're just going to go around the room. I'm just going to go around the room and ask. And if you don't know it, we'll just move on to the next person. No big deal. All right? There's no shame in that. So we'll start here, and then we'll just kind of work our way around. All right? Sound fun?
Yeah.
Sound exciting? Sounds fun to
Can
me.
you say the word pass?
Yeah, I mean, if you really don't want to participate, I'm not going to force you to. All right, so think about, here's what I'm asking, what I'm about to start asking. How do I draw curve 1 with this vector function? And curve 1 is this curve, which comes from that right there. Okay? So we'll do volunteers first. How about that? Any volunteers to figure out how we can draw that?
Wait, does volunteering help us skip our chances of being caught?
You won't be called again if you, yeah.
Because I haven't.
Go ahead.
I was thinking possibly replacing x squared with a lovely cosine t. Possibly, maybe in this way.
So cosine and sine are used to draw circles.
Okay.
Parabolas,
Oh, yeah,
unfortunately, are not circles.
That's right. Yeah.
It's a good attempt.
The intention's made.
Attempt was made.
That's all.
Go ahead.
It'd be x and then for y it'd be x squared. So you could do the vector function x and then x squared.
Okay, yes, but it has to be a function of t. So t, okay, so look, everyone pay attention to this. Anytime you have this is like our standard equation from like college algebra, right? Y equals a function of x. Anytime you want to use a vector function to draw a standard function that you've seen in the past, you just always let the x be t, and then the y will always just be that equation replacing your x with t. So t squared. Now you need to give me some restrictions on t here in order for this to happen, and those restrictions will be, so you got I'm calling, sorry, this time I'm calling. So if I want my restrictions to draw me just this, can you think just visually looking at this, what would t have to be to go from 0, 0 to 1, 1, right? Any ideas?
0 to 1.
0 to 1, that's it, right? Everyone agree with that? Okay. So t is the x, isn't it? T is the x. And so you want it from 0 to 1. Now the y is the t squared, that's this part right here. That's the y squared. Or sorry, the x squared. Okay, good. All right. I think we're good. I think at this point we're ready to set it up, aren't we? Yeah. Do you want to help me set it up? I'll help you out. I'll start out with the integral sign. Integral, right? So where to where? Okay. Now, what goes in here? So what's our integrand? 2. Okay, it's 2 from here, right? And then times x. What's that? T, right? Because for us, x is t. So this is going to be 2t. What are we still missing, though? Yeah, the arc length part, right? So all this crap. Square root of, all right, you know which pieces go here? Yeah, so it's the derivative of this with respect to t squared. So 1 squared plus 2t squared, which would give you 4t squared, and then dt. Perfect. Does that make sense to everyone? Yeah. Remember, this is our x of t. This is our y of t. So what we did was we took the original function and we replaced x with x of t. So that's 2t. Then square root, and